Good morning, everyone. This is our, I think, 11th webinar now on battery modeling and not different aspects of battery, right? And today also what we are going to cover is basically the battery modeling approaches, which are there different battery modeling approaches, and we'll also take you through the hands-on on RC modeling in MATLAB Simulink. So mix of session, interactive session, will keep it any point of time. If you have some doubts, please post them on the chat, right? And the chat also, we would like to keep it more interactive. I'll be asking you some questions during the sessions and all those things, right? So that your learning become much more profound. That's the whole objective, right? Let's start with this. And so this is the agenda for today. We'll be covering what is battery modeling, what are different battery modeling approaches, um, what are applications of battery modeling, understanding what is RC modeling, what are its components, right, and why it's done at the first place. Uh, and then we'll also do the deep dive in battery RC modeling with MATLAB Simulink, right? Speakers, me, Vishal Ahuja, and Lokesh Suri today are the speaker for this webinar. I'm co-founder of Techlands with more than 10 years experience in the electric vehicle industry. I worked with Mahindra, Vito Motors, Simple for a year, right? And I'm ideally alumni. Lokesh is also co-founder with Techlands. He has also similar experience, around 10 plus experience. He worked with Mahindra, ZF, Mercedes-Benz. He has actually around 10 to 12 papers also, and we are core technical people, and that's we like to take these kind of sessions. He's IIT Kharagpur alumni. So with this, let me start with the core topics. So if you see the first and foremost more important part of it, the battery modeling, the people who are very beginning in this particular thing, uh, uh, the most important thing is what is battery modeling, right? Because that's a physical component. Why at the first place you need to model a battery. Battery modeling is basically a creation of mathematical equations or computation simulations. So you can represent the battery pack while you are in designing phase. You while or you want to implement that battery modeling into the some systems. I'll talk about where you want like to implement it, right? So, but why the battery modeling is required? Anyone on the question, can you just chat on the put on the chat. Why do you think the battery modeling is required? Might be having some thoughts, right? Why we do the battery modeling in the first place? What is the application of battery modeling? Just post on the chat. What do you feel, right? Let me see the chat. Whatever you're feeling about why you do the battery mode, because this is something very important. Okay, some people think only that is the battery management system. Most application of the battery modeling, people think it's only in the battery management system. Can you think about other use cases? Okay, so I have to enable the chat for everyone. Yeah, I think, yeah, now you can actually put to everyone. Otherwise, it was directly coming to me. So please post to everyone so that everyone can see your question answers. So in the chat box, when you are messaging, please, I have enabled for everyone. I think that was disabled. So you can now post to everyone so other people can see your chats also. Right? Yeah. So some people mention, Sagar mentioned, predict the behavior in real-time environment, right? The simulate test instead of hardware. Divya mentioned. Dheeraj mentioned for efficient utilization of BMS in EV cars, right? Avnish mentioned to manage the thermal energy properly. Naushad mentioned performance prediction, right? Let's see this. So second, as people mentioned, yes, predicting the vehicle performance as well as lifespan, because the battery degrades with time. So you have to perform battery modeling to predict this behavior also, because in the real life application, you just cannot monitor it. You have to predict it, how the vehicle will behave in the field also, right? Then we have, as someone mentioned, for optimizing the design and operations, yes, the thermal modeling is done and the complete layout of battery is done to understand which cell is under stress, which cell is not under stress, so that like your battery can perform optimally in all the conditions, right? Yeah, battery model act as a digital twin, Rishikesh mentioned, letting us understand, optimize battery performance, safety, and lifespan, right? Let's talk about the safety aspects also. So, yes, especially from the safety perspective, people model the complete thermal runaway events also. This is very important slides to understand that each of these applications are very different. A single model cannot be used for all these applications. So battery management system, the modeling approach is very different. When you are doing the performance predictions and the lifespan, the modeling approach is different, the equations are different. When you're doing the design optimization, there the complete battery equation, battery modelings are different, right? When you're doing thermal runaway simulations, then it's complete electrochemical simulation, gas and all. These modeling approaches are different. So it's not like that's only one single modeling approach. For application perspective, from different application, you need to use different modeling approach. Were you aware of this fact? Yes or no in the chat. Did you know this fact that you have to use different modeling for different applications, right? Everyone, I would like to see, hear yes or no. Great, right? So there is no single size which fits all. Based on the application, you have to decide which modeling approach you are going to use. The people who are into embedded systems or into vehicle control system or they're building battery management system, they'll be working on single algorithm. People who are doing aging simulations, they will use different algorithm. Thermal people use different algorithms or different modeling approaches, right? And this the granularity also changes. I'll talk about it much more detail, right? So if you see the battery modeling perspective, there are multiple methods. One is empirical models, then you have equivalent circuit models, then you have electrochemical models, you have multiphysics models, then you have data-driven models. So these are different modeling approaches for different applications. Sometimes multiple things are mixed together to get the relevant results, right? In the industry, mostly these common three equivalent circuit models, electrochemical models, and multiphysics models are majorly used. Empirical models were long back used to be used. They are not used that much now. They're used for some extrapolations and all still, but not that much widely used. It, prominently, these three models, which are the equivalent circuit model, electrochemical model, or physics-based model, or multiphysics models, these are used. Data-driven also model are being slowly getting integrated, but not they are not so robust as your other three model, right? And for this data driven model, you need to have huge amount of data with you. That is something very important, right? So the mostly these models are being used. So what are these models? Let's go in deep dive into this much more detail, right? So if you see the equivalent circuit model, you might have heard about RC model, Thevenin model, quantum mechanical equations. These are under the equivalent circuit models. We'll talk much more about these things, right? Then you have electrochemical model where you model the chemical properties of the cells. That is cathode, electrode, anode, electrolyte, right? So there also you have single particle model, P2D model. You model as a continuum. You model as homogeneous model, particle scale model, heterogeneous model, because you can consider all the particle sizes same. That is called homogeneous model. When you model the particle size variation also, as well as the distribution and the gradients, that's heterogeneous models, right? So that depends on the granularity or the accuracy which you want to go in. We'll talk about that as well. Then we have multi-physics model where you would like to combine different physics like the mechanical properties, thermal properties, heat generations, and all those things. For example, the pouch cells, right? Please don't put something on my this one. Okay. Okay. For suppose pouch cells or these cells, what happens? Pouch cells swells, right? When the reaction happen or the charging process. So by using the multi-physics models, you can actually simulate these kind of behaviors. When you want to understand, my voice is not clear. Is my voice is not clear, Lokesh?
It's clear, Vishal. I think it's issue at
Okay.
some.
Someone messaged you.
No, it's clear.
My health is not a bit well, but I'm sorry for that. But I'm trying to give my best at this point of time. Okay. Then you have multiphysics models, right, where you have coupled electrochemical reactions, heat generations, thermal behavior. You can simulate the impact of venting of gases, thermal run, mechanical breakage, expansion of cells, and all those things which comes under multiphysics models. Were you aware of these things? Just put on the chat yes or no. Were you aware of these all the modeling approaches which are in the industry? Okay, great. Mix opinion. Great. Right. No worries. Right. Let us see and understand that what happens, why you have different approaches and what's the accuracy and complexity. The RC models are considered as lowest complex model, and the accuracy is not so bad. It's okay, but as if you compare with multiphysics model, their complexity as well as accuracy is very high, because you are modeling the complete physics, complete electrochemistry of those models, which is very important, right? Then you have computation speed. Once you are modeling very complex physical behavior of the cells, obviously the computation speed will be very low, right? Because it will take differential equation from multi-dynamics will be solved. And when you're working on very equivalent circuit models, that's how you get very high computation speeds. That's the reason the equivalent circuit model are being used in your embedded application and BMS design, system sizing, and all those applications, right? All the BMS algorithm which you use right now in the market on any electric vehicle uses equivalent circuit models. They don't use these physics-based models because they are very high. Computation speed is very high, and on the chip, on the silicon, you want the models to behave on very high computational power because you have less memory and you want them to react very fast because at the real time you have to take decisions, right? Are you aware of this fact? Again, yes or no, I want. So Tirupati, you joined very late. I think I already covered the battery modeling, right? So, okay. So equivalent circuit modeling are very good, but they have a application majorly in the embedded systems, in the BMS designs as well. When you go much more deeper, when you go for electrochemical design, these models are used for cell designing, battery design perspective, aging behavior analysis, battery health analysis. These algorithms generally don't sit on the embedded application, they sit somewhere else or in your simulation environment so you can understand the battery behavior in much more detail. That is where the electrochemical models are being used, right? Then you have physics-based model, multi-physics-based model. This is when you use for cell design perspective, whether my cell will crack, my swelling will happen, what my volume expansion will happen, how my complete battery pack architecture is my particular cell as having more strain compared to other cells, right? So all these things are done in multi-physics model environment. When you do this for detailed system design and R&D, where you want to optimize the performances to highest limits, that's where you do the multi-physics modeling of these things, right? So is this the application clear to all of you? Right? So which modeling we use for which application? Is this clear to all of you? Then we'll move ahead. I need yes or no. I don't want people sleeping. I know, I understand becomes very difficult sometimes to follow that sessions like this. Right? Great. Great. Nice. Nice to see everyone saying yes. Okay. Let's understand in much more detail what are tools being used for these application, right? So if you see this, for the simple equivalent circuit modeling, you have MATLAB Simulink, you have GT Suite, you have AMSM. This is used for system sizing as well as I mentioned you, right? Then for electrochemical modeling, we have COMSOL software, GT Autoline softwares, right? Then we have for multiphysics based software, you have COMSOL, ANSYS, Star CCM. These kind of tools which are available. This is full 3D, right? And sometimes it's a pseudo 2D also. These kind of things are possible. And full 3D gives you benefit of solving multiple things, right? And because you can see the pattern of fluid, you can see the impact of temperature gradients, you can see the volume expansion of the cell, the mechanical impact of the cell. Even if you want to understand when a crash situation is happening, right, what will happen to my cell, or the cell venting, the thermal runaway scenario, you cannot do in the thermal runaway scenario with this equivalent circuit modeling, right? You need to have multi-physics modeling to understand what's my puncture resistance and all those things. Kindly interrelate the application wise in real time. Uh, Can't internet the application wise. So this is application only, no, which I'm telling you. So when you, for suppose you want crash simulations, which you are doing it, right? When you want to understand my thermal runaway, like thermal runaway experiment, the puncture test, which was nail penetration test, that time you need these kind of models, because in the nail penetration test, you have a mechanical boundary, right, of the cell, where the mechanical property of will decide how much strength or resistance my mechanical structure is offering to the nail while entering. And once that enter it, how deep it's going that, right? And how that is breaking the layers. So that's multi-physics model, right? Chemistry is involved, your physics is involved, like mechanics is involved, multiple things are involved over there, right? And when you are doing the strength analysis of a cell, like for suppose be it a pouch cell or prismatic cells, when you're doing a strength analysis of those things, that time also need to have multi-physics model. So this is very important when you're doing cell designing or very high level of R&D. That time you need multi-physics model. Most of the people, it's 90% people use only the electric circuit modeling, right? So that is mainly widely used for the BMS applications. That's a major objective. Let's understand in much more detail. Let's go deep dive in one of the things, which is equivalent circuit model. Let's deep dive in that. So what are basically equivalent circuit models? So equivalent circuit model are basically when you're trying to model the electrical behavior by some common electrical elements. That's called equivalent circuit model of the battery pack, right? There also multiple elements. How it started with a very simple rent model, where you just model a voltage source and then you model a resistance, which shows a dissipation of energy. It started with the simple model when the equivalent circuit model of the battery started. Then it advances to Thevenin models, which had one series resistance and one RC circuit to model the dynamic behavior. So, what is the disadvantage of this one? This model was not able to model the dynamic behavior. Dynamic behavior means how the cell responses to the change in the volt current, right? Because the current, anyhow, we'll talk about it in much more detail. You will understand what is the polarization effects and all those things, right? This thing actually helped, this additional element helped to represent the dynamic behavior, but still it could not capture the very high dynamics environment. What scientists did, they added one more capacitor over here. What it did, it added the account. Someone is asking, is answers capable of multiphysics modeling? Yes, answers is capable of multiphysics modeling. Coming back on this, the PNGV model, apart from this series resistance and one RC network, the scientist added one more capacitor in between, which actually helped team to model the voltage changes to the accumulated charges. Accumulated charges means when the charge is accumulated on the battery pack, when you are doing the response of that, right? That time this capacitor helped you to model that, but still it was not so accurate. The last one which is being used is your dual polarization model or 2RC model. In this one, you have one series resistance and then two RC network. This helps to capture both fast and slow dynamics effect. And what is fast and slow dynamics effect? We'll talk about much more detail. It's very important to understand why we are doing this RC modeling from physics perspective also. Even though these are circuit electrical modeling, but there should be some physics, right, which you're trying to capture. So we'll go in that detail also today, right? So this is a basically 2RC modeling or dual polarization model, where you have one resistance, series resistance, and two RC network, right? Let's understand in much more detail. So there are three parts which model three different elements of a cell of a battery pack, right? So one is series resistance, one is one RC network, then second RC network. Sorry for that. Okay. Let's understand what each one of them been doing and why people were observing this. When a cell is given a charge or discharge pulse, the voltage response of cells behave differently. It has some linear component, some non-linear components, and all those things. So with this equivalent circuit model, we try to represent this, and Lokesh will cover in much more detail these aspects any which ways, right? I just want to give the overview at this point of time and the physics behind it. So the scientists wanted to, or the engineers wanted to capture these non-linear dynamics of the cells. And these three elements represent these components of a cell, the non-linear response of it. Let's understand what each one of them means. So the series resistance, one second, let me hide this, not hiding, yeah. The series resistance takes care of the linear resistance like electrolyte resistance, ohmic resistance, anode collector, anode connect collector, cathode connector collector, which are there. So all the ohmic resistance which are there, which are represented by this R naught, right? When you talk about R1 and C1, these are the fast dynamic responses. So when you want to capture the fast electrochemical process, means the ion transfer, the charge transfer resistance, this is represented by the R1. C1 represent the double layer capacitance. So what is double layer? I'll talk about the charge transfer and double layer capacitance also in subsequent slides. Don't worry about it. The R2 and C2 represent the slow dynamic behavior, the ionic diffusion of the mass transfer, like when the lithium ion moves from one place to another place. So this is basically captures that element. So what you try to do, most of the physics phenomena which are happening on the cell, you try to capture by this. Right? Just one second. I just drink some water. Not well today. Okay. So this is the phenomena, and if you remove this part of it, this element part of it, then you are not capturing the slow dynamics. You're not capturing the ion transfer. So I'll talk about ion transfer. Just hold for a while, right? And if you're not modeling this R1 C1 circuit, you're not capturing the charge transfer mechanisms, right? Which is your fast electrochemical process. So that's the reason our two RC models give you much more relevant answers because it captures your multiple physics phenomena, right? Let's see, understand what is this, and let's understand two things. What is this charge transfer and what the diffusion, right? Because there are two elements we'll talk about, fast dynamics, slower dynamics, right? So these are two important things which we have discussed. Please don't scribble on my screen, everyone, please. Right? So let's understand what is this fast dynamics and what is this slow dynamics, because are not every one of you understand, right? Yes or no? Extra capacitor is somehow related to SCI layer? No. The answer is no to that. Right. Is it clear what we are talking about? Any doubts you have? Is it making sense to all of you what we are covering as of now? Can you please put your answers to chat, yes or no? Would like to hear. Are you enjoying this so far? What we are covering, is it adding any value to you? Yes, yes. Great, great. So let's understand in much more detail, right? Now let's compare what is happening inside a battery. So there is an anode, there is a cathode. What happens during the discharging process? The lithium ions, discharging I'm saying, the lithium ions move from anode towards cathode, correct? And electrons move on the external circuit, right? This is, this thing, right? Little bit understood. Okay, no problem. We'll try to make you understand in much more detail, right? So what happens, let me just show you my, I think I should use some kind of pen and screen, so that will help you understand in much more detail, right? Let me use this, right? So what happens when your uh, battery is completely charged? So all the lithium ions are sitting on the anode side, right? This is our cathode side, correct? So this is my primary compound. There's the electrolyte in between. What happens when the battery is getting discharged? The lithium ion, they migrate from anode to the cathode, right? And the electrons which are there sitting on the anode material, right? They travel from an external circuit, right? So this is external circuit via which, and this is my consider resistance or some load via which the electrons are getting transferred. So from the compound of graphite and the lithium, right? Electron has to move from external circuit, and lithium ion has to move from this point to complete it. They have to travel from here to here, right? But electrons have to travel only externally, right? Now understand this, the size of lithium ion versus electron. If you compare the lithium ion size versus electron size, so this is a typical lithium electron, and this is typically your lithium ion. This is much more exaggerated. Actual size of this, let me just remove this for you so that at least you can see that. Oh, sorry. Right? So lithium ion radius is around 76 picometer, and if you see the electron radius is 2.8 factometer. So there's a huge difference, right? So if you want to see visually how does it happen, how does it feel like? So if you see when the ions are moving inside the anode, they move very slowly, whereas electrons move very fast, right? This is what happens, right? So because electron is very tiny and it's a charge, right? And lithium ions are there. They are carrying some mass, heavy mass, and they have to travel from an anode to the cathode. That is how we say this is fast dynamics, because this portion takes care of charge transfer resistance and double layer capacitance. Double layer capacitance is nothing between the solid and electrolyte. There is a layer of positive and negative ions, which are positive then negative. These two things combined make the double layer capacitance. That is later topic for later on. But this electrons phenomena is being captured by the faster dynamics by this R1C1 circuit model. But the ion transfer, the diffusion of ions, right? This is what is called diffusion, because the ions has to move from anode to the cathode, and it's a long journey for them, right? And there's a too much resistance in between. So this is called slow dynamics, because ions are big, they will take much time. Did you aware of this about RC model? Did you learn something new? Did you know this? This is basically what's the meaning of R1C1 and R2C2. Did you know this? Did you know that fact? Right? I would like to hear from everyone. Right? All of you. I would like to hear from all of you this thing. Right? So this is, people say it's RC modeling, but you should understand there is some physics involved in that. You're just not modeling the equivalent circuit. So you're trying to capture some underlying physics of the battery via doing RC modeling, right? And that's why this R1C1 circuit or R2C2, this is one faster dynamic circuit and this is slower dynamic circuit. And what they represent, this is something very, very important from physics point of view, right? So whenever you're learning something, it's very important to understand why you're doing what you're doing. It's okay, RC modeling is done, but what is the meaning of these circuits? What is the meaning of R1C1 circuit? What is the meaning of R2 circuit? And what this R naught represents? It's very important. And when you go for different chemistries, you'll understand this number changes and it will make much sense to you. If I talk about the solid state battery, right? So, if you understand the cell fundamental and cell details in much more detail, you will understand what will happen to these value without seeing the numbers, because you understand the physics, right? Let me go in this one, because these fundamental things are very important. Can you please describe that capacitor behavior in the process? So capacitor is double layer capacitor. Okay, Ajay, what happens? I was not intended to cover that, but let me cover that. There is something called double layer electrics, right? So let me just touch upon it. I'll not go in much more detail. What happened in your, please don't scribble on my screen, Sadashiv. Okay, unnecessarily it's getting, okay. Please don't scribble on my screen. How to end the show and restart again, stop sharing. I'll, 1 second. People don't scribble on my screen, otherwise we'll remove you from the session. Okay. Now there is something called double layer capacitance. What happened on anode side? So this is negative, right? What happens? and anode side, all the positive ions get attached to it. When the positive ions get attached to it, correspondingly, there is negative ions also, which comes close by to this, right? And in between this, there is some electrolyte. Okay, what happens? This particular phenomena is called double layer capacitance. This is called double layer capacitance. And this is much more prominent in liquid electrolytes. And this is less prominent because this is always forms in the interface of solid and liquid. So the double layer capacitance always forms on the interface of solid and liquid. Okay, I can tell you about this much only because this is a very detailed topic. I'll not go in detail of that. Right. So this double layer capacitance, which is what you're trying to model in this particular phenomenon, the faster dynamics, right? In the diffusion mechanism, the ions which are there, right? The ions which are there, they get diffused very slowly. So that is called the diffusion capacitance. I hope this is clear to all of you, right? Okay, so I think we are getting late now. Yeah, I have to transfer to Lokesh also. I think Lokesh, the 2RC modeling part now you can take it up and you can take it from here. And I think Lokesh will tell you. Lokesh, you're there?
Yes, sir. Then
Yeah.
just a second. Yeah, thank you for the insights. Okay, just for flow sake, I'll go few steps back. Okay. Uh, but meanwhile, let me share my screen first. Okay, is my screen visible? Can you see my screen, Vishal? And am I clearly audible? Hello, am I audible?
Yes, Lokesh, you're audible.
Okay, good. Okay, let me go a few steps back. I mean, why are we doing this, all this, right? I mean, since years batteries are used in vehicles, and now suddenly when EVs have come, we are, talking about battery concepts, battery modeling algorithms and stuff, right? So, I mean, there are broadly two main reasons. One is safety, another is, the usage part. So, the batteries which were used earlier were not the main, energy source in the vehicle, right? They were just supporting some auxiliaries. But now in EVs, instead of fuel, they are the main source, right? So here the safety part comes. If we don't, develop battery pack properly, there could be mishaps, right? That is one major reason. Other is, right, like if I develop some battery, if I put some battery in a vehicle and then after 2 years I have to replace that pack, cost for it is too high, right? So as engineers, we have to take care of it, right? If these two reasons had not been there or had been sorted, the bigger, things to, think of in life would be what are the new things in Flipkart sale or where to go, Shimla or Goa. But safety, is one important thing now in EVs. And how do we optimize the usage of battery in terms of health, in terms of longevity, right? So because of these two main reasons, we have to deep dive into battery concepts. We have to understand how to model a battery. We have to understand how to do algorithms around the battery pack, right? Vishal has already explained about different modeling techniques and uh, why they are required, right? And we, I think, have now a decent idea, a fair idea of why RC modeling is required, right? I was going through the comments in the chat and I realized that there are few people who are like now very new to battery concepts and now they are gradually picking up the concepts why it is required, why it is not required, right? Uh, I'll switch between two windows. One is paint window, that would be our whiteboard, and another is MATLAB window where I'll show the RC modeling part. I'll implement that. Okay. Before doing the RC modeling, one quick concept again, why simulation? So now let's say I have a vehicle. This is my car, right? And I have to put a battery pack here, right? Now, when I develop a battery pack for a car, if I start doing everything, from day one at hardware level, I will have to develop a lot of hardwares, right? A lot of battery packs, physical battery packs. Now, that is uh, time consuming, and more importantly, it is risky. Risky as in, I don't know the extreme behavior of this battery pack. Let's say the first battery pack which I'm using, I'm riding the vehicle or driving the vehicle at extreme, and then some extreme limits got breached, and fire would be there, right, in the pack. So it's risky, right? So what we do is we do simulation. We try to uh, understand things as much as possible in simulation environment, and yeah, that is the main reason why we do simulation, right? And then other part is algorithms. How do we develop algorithms? uh, so algorithms, it's more effective to develop in simulation environment and then try it on hardware, right? So I mean, because obviously we have physical battery pack, why do we want it in simulation environment, right? So normally when it comes to battery related work, uh, when it is RC model battery pack, so it is like RC model here of battery. So this is my battery pack. This is my simulation window, okay? Simulation environment. I would develop this model properly, and then I can develop algorithms, algo 1, algo 2, and right? Algo n. Understanding it, uh, oops, sorry. Yeah, understanding it at a vehicle level. This is my battery pack, which is, mimicked at this place. And I would have, BMS sitting somewhere to control this battery pack. Battery pack is a dumb thing, right? It is BMS which controls its operations. So BMS algorithm, the algorithms which would be in this BMS would be, here in the simulation environment. So we develop algorithms, we put it in the BMS, and to develop these algorithms, we should be knowing what on like these algorithms would be controlling what, right? So it would be this battery pack which we want to control the operation part, right? So we need to mimic this battery pack, and RC modeling is one of those, more popular methods because it is first of all pretty close to mimic the battery behavior when it comes to uh, you know things required for simulation level. Other is it is quite light at simulation level, so it doesn't need too much of simulation time. We can emphasize more on the algorithm development and not on the battery pack modeling, right? We really don't care about what is happening at chemical or chemistry level inside it. All we need to know is what is happening at voltage, current, and temperature level in the pack, right? These three things are mainly or mostly enough, when it comes to developing algorithms. Okay. So yeah, this is a reason why we are doing RC modeling. Coming to RC modeling, one second. Okay, another paint window. So we have understood, right? This is like how RC model looks like. Quick things. Why resistance and capacitance only? Why not inductance? Why not a diode? Right? Because the intent here is to mimic battery's behavior, right? So if you take a battery or for that matter, a cell. So when you take a cell, it would have some voltage in it, right? Some potential. This voltage is mimicked by this. Okay. Now, when you draw current out of it, okay, this current to a load. So through a load, when you draw current, what you would see is you can draw current like this. If you want, suddenly from 0 ampere, you want 4 amperes. Uh, you can draw current like this. Okay. When you draw current, if you monitor voltage at these terminals, okay, for your reference, terminal voltage is different from the battery potential because there is impedance inside battery or cell. Okay, when you monitor voltage across the terminals, what you would observe is the voltage behavior would be like this, which Vishal showed in the slides also, right? The intent here is very simple. We want to mimic this behavior, right? Now, it can be RC circuit or it can be some ABC element, which also, if it is mimicking, we can actually use that also, okay? But what we realize is current can be immediately drawn, so inductance is not required because inductance is or should be used when there is an inertia in current flow, right? But in this case, we see inertia and voltage flow. Voltage doesn't, immediately drop. There is sort of this dynamics, right? Which we see time constant dynamics. And to mimic this voltage dynamics, RC combination is the combination in, uh, you know, electrical circuit, right? So that's why these RC elements are here. Okay, and then the underlying physics anyway we shall told. So there's something called time constant, which is nothing but multiplication of RC values. Okay, the details of this we cover in our course, right? So here intent is to just get a brief idea of why RC modeling, how to do it, right? So someone was asking how to know these RC values. So there are multiple tests. One of the popular tests is HPPC test, where you take a cell, you put it under test, and then you take, do sort of pulse discharge in the cell, okay, till it is fully discharged, from full charge to full discharge. And then what you see is there is a behavior of voltage like this. Sorry. So it would just keep falling like this with these pulses. So from this data, as you know, this is RC behavior. You would be deriving all these R1, C1, R2, C2, and RS values. Okay. For better feel, let me. This is the last thing. Then we'll go to the simulation window. So how do we derive the RC values? So when you put cell under test, you would be taking pulse discharge, right? And then what you would be finding is there would be voltage behavior like this, right? Okay, one second. There is this thing disturbing about stamp. Yeah.
Lokesh, in the presentation, one slide is also there if you want to show on HPPC test. Slides are
Yeah,
there,
I mean,
right?
I am just avoiding switching. I mean, this is the
Okay.
last thing. Uh, then we are anyway moving to simulation window. So when you see this sort of voltage behavior, this sudden drop, if you understand the circuit, this is coming from the series resistance, right? Similarly, when you take off current from the load, or you don't take off load from the circuit, there is again this sudden jump. So this is resistance into current behavior. So this drop is because of the series resistance because it is immediate drop, right? While this behavior, if you see, if I try to understand this dynamics, what you would find is there are two dynamics. One is like faster dynamics in this, and then another is you know slower dynamics in this. Okay, Th- it is, I mean, actually quantified through time constant concept. So faster dynamics actually help you deriving R1 C1, slower dynamics help you deriving R2 C2. Okay. So y-axis is nothing but R1 plus R2, and then this time constant concept helps you with deriving the C values. Okay. So this is how you derive RC values through the test. You put your battery pack or cells under test, and then you get this data, and then you derive RC values. Okay. Parameter estimation sort of thing is happening here. Okay, I hope it is clear. Let me just quickly check chat window before going to simulation window. Yeah, there is a question, what is the main why RC modeling is mainly done? Okay, let me answer this before going to the simulation window. See, RC modeling is mathematical modeling, right? You have RC elements, and then you actually can put it in differential equation form also, because RC, if you put it in voltage current form, you would ultimately get differential equation from it, right? Now, this differential equation helps us in multiple ways. One is to understand any system's dynamics, its limits in terms of frequency behavior. I cannot go into the details a lot. We are covering these things in our course in detail, but in 1 hour it cannot be covered. When we want to understand a system's behavior in frequency terms, because at times or many times or most of the times it makes a lot of sense to understand systems behavior in frequency domain rather than time domain. uh, it becomes easier from frequency domain analysis to understand what sort of control should be done, what would be the extreme behaviors, the limits, the bandwidth. Okay, so RC modeling helps us converting the model into differential equations. That helps us to understand the limits of the system in frequency domain, and that gives us better clarity in terms of what sort of action should be done or taken when we develop algorithms. So, single sentence answer, we use RC model mostly when we are developing algorithms, various algorithms like SOC algorithm, SOE algorithm, SOH algorithm. For these algorithms, RC modeling is very important. And as I said, because before implementing these algorithms, this RC modeling helps us to understand the behavior of the system in frequency domain. Okay, so there's something called Laplace transfer function and stuff in control system concepts. These things can be done with RC model, because voltage and current behavior can be converted into differential equations. Differential equations are in time domain. These things, then differential equation can be converted into Laplace form. So it becomes easier to understand things in frequency domain. Okay, because one last thing before I go to simulation window, when it comes to step response, there are infinite frequencies in this. Okay, when I come to this behavior, there are some frequencies which are entertained by the model, there are some frequencies which are not entertained by the model. So it's a slightly different or parallel world when it comes to understanding things, but then when it comes to algorithms, control system, people find this to be more useful, sort of world to understand and do algorithms development. Okay, let me switch to MATLAB window now. We'll do RC implementation. So this is our MATLAB window, uh, where we would open Simulink. Okay, and the RC circuit we will implement here. Okay, so I've opened a blank model here. To save time, I'll switch to another window, but before doing that, I'll just explain how to use this, window. So there's something called library browser here. You have to click here, and then you would find multiple, block sets, different type of block sets for different applications. For RC modeling, we have to go into, heading called electrical systems, and there we will find all the elements. So MATLAB is quite vast. It caters to different applications. So when it comes to our RC modeling, there is this thing called Semiscape where we have to, yeah, if you click on the drop down, and it takes time also. Foundation library, there is this thing called electrical and electrical elements. You have capacitors, you have resistors, you have inductors. So from here you would get all the elements. Okay, all you have to do is you have to click on this, drag to the window. Okay, and like this you can get all the elements. Sorry about this. There is some lag in action versus responses. So like this you would drag the elements. Okay, to connect and make the circuit, you have to just use your mouse cursor, connect it like this to put the values. You have to just double click. Yeah, please bear with me. At times it is slow. Yeah, this window would pop out and you have to put the values here. Okay, I told how to derive the values. It is done through test, measurements, parameter estimation. Okay, so now we will implement this RC model and we'll see the behavior what Vishal showed to us. Okay, oops. Right. So what I normally do is RC model battery. I'll search it in Google. I'll open images. I'll take some image for my reference, and this is exactly what I would do. So what do I need? I need three resistors, two capacitances, and one voltage source, right? So we saw how to do that. Go to library and search for those elements here. So there are three different ways to get these elements. Either you can search it at this part, enter search item, or you can navigate to that section and then take those elements from there. So I'll do first through navigation part. Capacitor I'll get, right? So two capacitances. Then I need resistance, three resistances is what I need, right? So yeah, right click and drag, you would get another element. So these three things we got. We need a voltage source, right? Uh, where do I find voltage source? Electrical source sensors and voltage electrical sources. Okay. We have to pick DC voltage because we are trying to mimic here cell behavior, right? Okay. This is what we would pick. Okay. Quickly doing the connections. I mean, when it comes to implementation, it is as simple as this, right? We just have to open that image. We have to just mimic that connection, what is there in the image. Okay. And then you can connect all these. So just for, saving the time, let me open that model directly for you. Or maybe we'll do it and then I'll show the simulation part from there. Okay. So you have to just, drag and connect things like this. Okay. For the aesthetics part, I mean, it doesn't matter the distances, put on the upper side or capacitance as long as they are in parallel. Yeah. And yeah, this should be the negative terminal. So we need to give a ground, okay, also to make the circuit understand the reference point, okay, for any measurement. So we have this thing called electrical reference, which goes as ground, okay. a load has to be connected. For now, I'll just take a resistive load. Okay, I hope my screen is visible. It's not too small. Let me know if it is. Yeah. So load would technically go like this, and other part would go to this terminal, right? So this is my circuit. One quick thing, there is something called solver configuration. Details, if one wants to understand, can go to the help section. But basically, for this MATLAB to run this whole circuit, it needs to understand uh, in the back end what it should be doing, right? And as I told, these things can be converted into differential equations, and that exactly what MATLAB also does. It tries to do this in differential equation form. So we need to tell that you have to do it in differential equations. So we connect this thing called solver configuration, where from where it figures out which solver it should be using for differential equations calculations. Okay. So this is our two RC circuit, basically what we have. And Shubham, please don't do this. Vishal, how do I remove this?
Now you have to stop sharing and then reshare. Shubham, to all of you, please don't. I think it's gone now. Lokesh, it's okay.
Okay,
People, please don't do this. It is becoming troubling some for us also.
right. So if you see now at the image, we have voltage, resistances, capacitances in this sort of combination, and then these are the two terminal points where we can uh, connect the load, which I have done by connecting this resistor. Just to understand that pulse discharge behavior, what I would do is I would uh, activate this load only when I want to. Okay, so what I can do is I can put a switch here. So with this switch, I would actually do an intended trigger whenever I want to uh, do this, uh, want to connect the load. Okay, so this switch is sitting between the load and the circuit. This is the point from where I would trigger the circuit. Okay. So how do I trigger? I need pulse, right? So now the other way to search that pulse block, what you can do is you can just do, you can click on this window like this and then directly search pulse. You would get something called pulse generator. Okay. I can decide what sort of pulse I want, how much, for how much time it should be on, how much time it should be off, right? So if I double click, amplitude, let's say I want to do a discharge of 10 amperes. Period, let's say in case of cells, you will understand the dynamics. It is normally the relaxation where the voltage takes time to settle. It is in minutes, right? So normally it is, you put around 1500 seconds at least. Pulse width, discharge pulse, let's say, is of 10%, and rest is all, you know, pulse off state. So like this, I would decide the current required by the circuit. Sorry, my bad. One correction. This pulse generator is just to trigger the switch. So current will be decided based on the resistance value we have. Since I very regularly use this pulse generator for deciding the current, I said that. So amplitude one is fine to trigger this circuit. Okay. Now, if I connect this thing, it will actually not connect. The problem is this all these block sets are taken from this section called SimEscape, right? I just hovered to this section SimEscape in this whole big library. While this pulse generator, it is in a different section, uh, which is in this first uh, heading Simulink. And if you click on the drop down of sources, you will find pulse generator somewhere here. So these are not directly compatible because one is mimicking physical system, other is equation based thing. So it's a very MATLAB thing to make them compatible. There is something called Simulink to PS and PS to Simulink. So this is the block where which all you can consider or you have to take to connect these two blocks. Okay, it's just an interface. There's nothing, there's no concept behind it, as in it's a MATLAB sort of thing. So MATLAB thing. Okay, the response is slightly sluggish. Okay, last thing it was anyway. So this is how your RC network can be implemented. Putting the values I'll show from the existing implementation, but now this should be running. Okay, I'll just select and comment out and take the model which I've already created to save time, and we'll understand the behavior from there. So this is something which I already created, RC model. If you see here, I have put a switch here, which is actually connecting this load resistance uh, with this RC network. Okay, this ammeter and this voltmeter is to monitor voltage and current. Okay, uh, so if you see the values, I have put these values which are how do I say, the values which you find in your lithium ion NMC cells mostly. Okay, so all these resistance capacitance values are taken from there. Okay, today it's slower than yesterday when I was actually implementing. Okay, so I have put the values here. We'll quickly do one simulation and see the behavior. Right. So if you see voltage at cells terminals, when I am drawing current of 0.5 ampere, the voltage is dropping suddenly initially. Then there is sort of a time constant behavior where voltage is dropping further. And when I stop drawing the current, voltage jump again is there, and then there is this behavior. Okay, so I'll take a snapshot of this and then discuss concepts on this graph only. So when current is taken out, there is a sudden drop, right? So if you see our circuit, this is our voltage, then we have resistance, series resistance, then we have RC elements, right? So this is our series resistance, this is R1, R2, C1, C2. So this thing is because of RS, okay? So if this amplitude is lesser, if this is bigger, depends on the RS values, okay? Whoops. Did I stop sharing screen?
No, Lokesh, it's visible.
Oh, it's visible now. Yeah. So this is because of RS, this sudden drop. Then this thing is because of R1 C1, R2 C2. The better place to understand this behavior more is this section. This is called relaxation area. So you see voltage is relaxing in this much time. Even when the current is stopped at this point, it is taking almost this much time to for voltage to relax, right? So if we decode it properly, like, you would find two dynamics in this, a faster dynamics in this, and then a slower dynamics in this. The faster dynamics is from R1 C1, slower dynamics is from R2 C2. Okay, so this is how basically your RC network implementation is done. To RC model of the cell, and you see the behavior. Okay. Use case of it, once you have this cell model, and when you put, I mean, if you want to mimic battery model, you have to just scale it in terms of voltage and current. Okay. Once you have this RC model, you have your battery pack. And one second. So I'll again take a snapshot of this window. In the beginning, I uh, explain this, right? Where I compared it with actual vehicle thing. So this is my actual vehicle, car. Uh, Pardon me for my sketching skills. So I have my battery pack here. I have my BMS sitting here, right? So this battery pack is mimicked by this RC model. Now I can develop algorithms around it. I can develop SOC algorithm. I can develop SOE algorithm. I can develop SOH algorithm, right? All these algorithms can be developed and simulated on this RC model which I have developed. Okay, so these algorithms uh, are developed next to it. We develop these algorithms and then generate code out of this algorithm and put it in BMS. Okay, so this is how this whole loop works from simulation window till vehicle level development. Okay, if let's say the algorithm is not working properly on the vehicle, we come back to the simulation environment, see, do the changes in the algorithm. Let's say SOC algorithm version 1 is not doing, uh, not giving proper responses. So we will do SO development. V2 will be developed. It will be simulated on this model, and then we generate code out of it and again put it in BMS and check it at vehicle level. So this is basically how things happen in end to end. Now, other thing which I want to highlight, which I mentioned, that it is not the circuit level behavior which is of more importance. Actually, RC behavior is understood in frequency domain, as I told. So we actually convert it in equation form mostly, and then try to see the behavior and then develop algorithms with that model. So this other part which I have developed is that thing, details of how to convert a circuit into equations, differential equations, and then Laplace domain transfer function form. Uh, Cannot be covered in 1 hour, but we are covering these things in detail in our course. So this is just to give you a feel of how a circuit and how its equivalent, Laplace domain or frequency domain thing can be implemented. Okay, so what I've done is I've taken the circuit, RC circuit, like this in this combination, and I derived equations of this RC circuit which is inside this transfer function. So it is Laplace domain transfer function implementation where I have a feedback loop, and then this transfer function is mimicking this whole feedback loop along with the transfer function is mimicking this RC network. So this lower part is equations, this upper part is circuit, right? So if I simulate this, so what you would see is which is enough. We are monitoring voltage from circuit and voltage from equation implementation. Yeah, few minutes, extra minutes are going because of this slow response. Yeah. This final thing, guys. I'm just trying to zoom this in. So I don't know if you can see, basically both the responses are overlapping. The intent is to show that uh, the same circuit-based implementation can be mimicked through equations, and that is actually the uh, more popular approach where you convert your RC network into equations, understand the frequency domain behavior. So if you see purple and the yellow one, it is showing that both the behaviors are same. So that is what I wanted to highlight, that this a circuit implementation can be converted into a transfer function form based implementation, and then this lower part is more sensible thing when it comes to developing algorithm. This approach is more popular, and this is what we actually cover in the course when we develop algorithms like SOC, SOH algorithms. So that we understand the limits of the system, we understand the dynamics of the system better. Okay, so summarizing the things, we have implemented RC network. It is as easy as this, where you open RC model image, You just mimic this sort of implementation in MATLAB window by dragging and connecting the elements. You have to double click, put the values. How to derive the values, I have explained. HPPC test and few more tests are done to derive the values. So once you put all these things, once you put all the values, your behavior should be mimicking actual battery pack behavior. And how much it should be, it depends on the use case again. Uh, Normally thumb rule is like 90% plus correlation is good enough. Depends on the algorithm. For state of health algorithm, which is a slower dynamics, it takes multiple charge discharges to do it. It is okay to have a simplified RC model, but when it comes to SOC algorithm, we try to have more sophisticated RC model. Okay, so it depends on how much it should be matching with the actual battery pack. It depends on the algorithm which you are going to develop around it. Okay, so yeah, this is how you do RC modeling. This is how you use RC model further. I have told that circuit level implementation is more for the understanding part, but when it comes to developing algorithms, it is mostly equation-based development, because then you open the world of stability, the response behavior, the frequencies the system is entertaining, frequencies it is not entertaining, or noises. All those things are analyzed better in equation form. So RC model or any circuit uh, is actually converted into differential equations or Laplace domain transfer function form, and then we do the further developments. Okay. I hope everyone got a feel of how this RC model is implemented and how it is used further. Okay. If there are questions, maybe for 1 or 2 minutes I can answer them. Otherwise, over to you, Vishal.
Yeah, meanwhile, let me share my screen and let them pose the questions if they have. And I think let me know, Lokesh, if my screen is visible.
It is. I think there is one question only which I have to pick.
Sure,
Can you
please take.
explain again what battery modeling means? Battery modeling, again, as I said, uh, I I have an actual vehicle, right, in which battery is there. Now that battery should be controlled in terms of operations, how much current I should draw, how much, in what voltage range I should be, what we say, operating it in. So to understand all these limits, values, I need to, do simulations, understand, develop algorithms. So to add in simulation window, when I'm developing algorithms, I need a battery, model, right, to mimic actual battery's behavior. On that mimicked battery, I develop all the algorithms, see everything is working in simulation environment, and then those algorithms I put it on actual vehicle. So that is why we need battery modeling. Okay, Vishal, over to you.
Yeah. So I hope everyone has more clarity on the things, topics, RC modeling especially. So there are some tests which are there to complement. Uh, okay, so some questions are still there. Like I think we'll be answering in the
No, no, I'm
session.
answering. Yeah, please carry on,
So we
Vishal.
have OCB test, OCB versus OCB test. There's a process for that, and then we have HPPC test. So someone asked, "What is HPPC test?" Right? So let's understand HPPC test, the process of it. As Lokesh already mentioned to you, we give a pulse discharge, right, or pulse charge. So if you see this, we prepare a battery pack. What you do is you let me use my pointer. You keep the battery in rest condition for 60 minutes. Now this rest condition is very important to voltage to get stabilized across, right? You measure the initial as OCV of the voltage, OCV of the pack, which is open circuit voltage. Then you give a pulse current of very short duration. If you see, this is a pulse current which is given, and based on that pulse current, you see the voltage response of that. Then again you rest for 10 minutes. Now why you rest for 10 minutes? Because again there's a relaxation time, right, for this. So you have to bear with that. So you give a pulse, you rest for 10 minutes, then again you give a charge or discharge for next step, and then you analyze this. So this is basically HPP test overall. So in overall process you do it, keep on doing it till you have this response of voltage at different SOC values. This is how the HPP test is performed, and then you have a response at different currents also, different temperatures also. But this is the basic fundamental of SPPC test, right? Which is important. At the end, what you want to get, what the point, what Lokesh also mentioned, after this analysis, you have to fit the curves to get this R1 C1 and R2 C2, right? Which is important from this perspective. Uh, at the end, whatever Lokesh showed you, he rightly inputted in the simulation tool. You have to extract that from the cell testing. Okay. So cell testing also becomes very important when you have to understand the battery modeling approaches, right? I think this is already done. Now, I think we are end of the sessions now. Let us help you understand what we do at Techlands, whatever this one is. So Techlands is an focus ecosystem of EV development. So we provide training programs. We give you, along with the training programs, actual hardware, because we believe in learning happens on actual hardware. When you do the things, you build the things by your own. We also provide engineering services. Apart from that, we also conduct these kind of webinars and blogs for free. We don't charge anything for that, these kind of learning sessions, because this is something we strive for to develop the technical community, right? And I think most of you are also part of the EV engineering community, open source community, where you can brainstorm on the ideas and all those things, right? So this is something important for us. So we have a complete ecosystem, and we also help you with the product development that comes under engineering services domain. Okay, so what, and we are startup which is government recognized startup. Okay, we are registered under MSME and Startup India certified company. And I think this we already told you, me and Lokesh are the co-founder for this company, and we both are from IT alumni and work with industries for more than a decade now. That's how we bring our knowledge from that industry experience, not from academic experience, when we take these kind of sessions. And the training programs also what we have developed are purely from an academic industry perspective, not from academic perspective, right? So okay, so what are the and you can actually take our website, go to our courses.